Hi, this is lesson 7 on reaction rates. This is the first lesson in our second section, which is on kinetics. This will not be on test 1. All right, so there's some information on the top, including SI, Mondays and Wednesdays, tutoring, which is almost every day of the week, and evening, morning, whenever you want. So go ahead and look there. One note is I will post information, a video with information on quiz and tests, April 20th. And then I'll have information on the quiz, test, and also about the review. Because our first quiz is on the 22nd. You're going to do that through Blackboard. There will be a review on Friday, April 24th. And then test number 1 on lessons 1 through 6, not this lesson forward, that will be on Monday, April 27th, and that'll be through Sapling. All right, so go ahead, look at that video. If you have any questions, let me know. All right, so we have a little bit of a review. This is from lesson number 6. This is stuff that we will be on test number 1. All right, so first we ask about Gibbs free energy. Remember, Gibbs free energy tells us if something is spontaneous or non-spontaneous. If I have a delta G that's negative, that means it's spontaneous. A delta G that's positive, that means it's non-spontaneous. And remember, spontaneous means it will occur at those conditions. Non-spontaneous means it won't. Okay, what about if something is endothermic and decreases entropy? For this, we need to remember that delta G equals delta H minus T delta S. All right, so if it's endothermic, that means that delta H is positive. And if it decreases entropy, that means delta S is negative. So if a positive minus a negative, that's going to give me something that is always positive. And if it's always positive, what that means is it's going to be non-spontaneous. All right, number 3, we have a positive delta H and a positive delta S. In this, we need to look and we need to see, hey, at certain temperatures it's going to be spontaneous, and at certain it won't be. And in this case, it actually ends up being spontaneous only at high temperature. Because remember, it's delta H minus T delta S. So that minus sign means that, hey, the higher the temperature, the higher that term is, and that's going to make my delta G negative. All right, the last one is actually a calculation. Let's go ahead and do this one real quick. So if I have delta G equals delta H minus T delta S, I tell you that delta H is 20 kilojoules. So I'm going to go that minus, my temperature is 500 Kelvin. And my S, my delta S, which is change in entropy, is 20 joules per K. All right, so this is going to get me 20 kilojoules minus 500 times 20 is going to get me 10,000 joules. And I need to be careful because what I need to do is I need to convert from joules to kilojoules. And so this gets me a delta G of 10 kilojoules. This is non-spontaneous. All right, so what we have to do is always remember it's dependent on these 3 things, delta H, T, and delta S. If you want, go back to lesson number 6 and review this. This will be on test. All right, so let's move on and let's talk about kinetics. So kinetics is the second section we're going to talk about. We started off talking about thermodynamics. Now it's kinetics. And kinetics is talking about the speed of a reaction. So in 215, we talked about stoichiometry. That's the compounds or elements involved in a reaction. Then in thermodynamics, we talked about the heat involved and whether something's spontaneous or not. Kinetics is what we're going to talk about now. And so chemical kinetics is the study of the rates of chemical reactions. And so by rates, I just mean speed. So if I say, hey, what's your speed? How fast are you driving? I can also say rate. All right, so let's think about this. So if we had combustion of propane in 215, we learned that propane, which is C3H8, it's combustion, so it has this reaction here. We know it's exothermic. That means delta H is positive. There's a lot more disorder afterwards, so delta S is also positive. And so I could do the math, and that would give me always delta G of -0 or less than 0. That means it is spontaneous. If I look at a different reaction, the formation of ammonia, this comes from N2 and plus 3H2 going to form 2NH3. This is one of the precursors in making fertilizer. Well, this is also an exothermic equation, but it has a delta S less than 0. And we could do the math and we could find out that it's spontaneous only at low temperature. But there's a other difference between these two reactions. Okay? This reaction here is very fast. If all of a sudden this starts to catch on fire, what do? I run away. I'm not going to stay and say, I got time. No, I'm either going to try to put it out or get out of the way. This reaction is slow. And speed matters. Speed matters because I want to know whether I should run away from this burning table and whatever the heck else is on there. But it also matters if we're looking at industrial production, right? Or in a lab. We want to know, in a lab, you always want things to be faster, right? So I want to make sure this reaction can be as fast as possible. All right, so let's talk a little bit about speed or rates. Okay? So let's say I'm in San Bernardino, I want to get away, right? I can look at my speed, right? Let's say I go 60 miles per hour, right? This I could also say as meters per second, right? This is actually the speed of light, c, right? I can't drive that fast. Speed is always distance over unit time, right? So a distance here, miles, here it's meters. Here it's hours, here it's seconds, okay? And so what I can do is, let's say I'm going to drive from San Bernardino to Barstow and then eventually to Las Vegas. Right? It may be that there's a lot of traffic in this area, right? There are a lot of cars. If I were to look this up on Waze, it'd be red, right? And so I can only go those 70 miles in 75 minutes, right? So 56 miles per hour. I just do miles over minutes or over hours. And then I go from Barstow to Las Vegas. It opens up, and I go really fast, or faster, not really fast, 78 miles per hour. Now, notice when I'm doing this, my speed varies. At the beginning, I'm going slow, and then I speed up. Now, this would be my speed at any given time, right? Now, between Barstow and Las Vegas, I'm probably not going that entire way at 78 miles per hour. Sometimes it's 78, sometimes it's 80, sometimes it's 90 miles per hour, right? But I can have what are averages. And I could also figure out the average speed for this entire way, right? By summing up all those miles over the amount of time, and I get my speed. Well, in this class, we're not going to talk about speed and distance per time. We're going to talk about them as reaction rates, which is change in the amount of a reactant or product, okay, per unit time. So per second or per minute. Okay, so we can figure out this change in amount of a reactant or product in a number of different ways. One way is we could talk about moles or mass. If it was gas, we could talk about pressure or volume. Sometimes if it's a colored solution and the the color goes away, I could use color to tell me about how much there is. But in this class, typically, we're going to use concentration. And we're going to use molarity, right? Remember, molarity is moles per liter, okay? And we can signify concentration by putting brackets, okay? So this means the concentration of H2O2. All right, so make sure, if you forget about this, go back to 215, look at your old notes, make sure you understand, because the rest of the quarter we're going to be dealing with molarity a lot. Okay, now that's the top part of it, the change in concentration. We're going to use molarity. What are we using for the bottom part? Well, we can use seconds or minutes or hours, depending on how fast it is. If a reaction is really fast, we could talk a bit about in seconds. If it's really slow, instead of saying, hey, how long it happens in 1 second, we say in 1 hour, right? In the same way that here, this is for a car. A car is fairly slow in comparison to the speed of light, right? So for something that's fast, we may do how long does it travel per second? Here it's per hour. Okay, so the units of rates or reaction rates is always, or we're going to use, is molarity per second. We can also write this as moles per liter second, or moles, liters to the -1, seconds to the -1. We're going to use all three of these. They all mean the same. All right, so let's look at a reaction and let's figure out reaction rates. All right, let's say we have a very simple reaction. A going to B. Okay? So I start off with A. That's the black circles. You can see that all I have is A. Right? And if, let's say I say this is 1 liter and each dot is 1 mole, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 moles of A in 1 liter, so that gives me 10 molar A. I have no B, so that means I have 0 molar B. Okay? So now I can look at this and I can say, all right, this reaction is going to occur. Well, let's say 50 seconds later, I look at this and I say that, hey, now I have 2, 3, 4, 5, 6, 7, 8 moles or 8 molar A, and I have only 2 of these red diamonds that signify B. Okay, so I have 2 molar B. So I could ask myself, how fast is B being produced? Another way to say this is, what is the rate of formation of B? All right, so what we're going to do is we're going to write some rates. In the same way that when we're dealing with speeds, we may go, hey, distance traveled over seconds or hours, whatever. We're going to do the same thing with rates. We're going to talk about the change in concentration of B over the change in time. Remember, change always is final minus initial. All right, so my final concentration of B is 2 molar, but I start off with 0 molar. So that's 2 molar minus 0. And my final time is 50 seconds. I start off at 0 seconds. So that's 2 molar divided by 50 seconds. Or 0.04 molar per second, or 0.04 moles per liter per second, right? These things both mean the same. All right, so on the right, I'm going to write down some reaction rate rules, okay? The first rule is that if I ever want to know a reaction rate, it's going to be the change in the concentration of X. In this case, we're looking at B, but I put X to mean anything, over the change in time, or delta T. Okay. Now, I could also ask, in the same way, how fast is A, compound A, being removed? And I could say this, what is the rate of decomposition? So whenever I say rate, I'm asking how fast or what speed is it? All right, so now I have the same thing. I have AF minus A initial over T final minus T initial, right? That's delta A over delta T. But here's my second rule. Whenever I deal with reaction rates, they must be positive. Okay? So what that means is when I deal with reactants, because reactants are decreasing, I need to put a negative sign here. Okay? So I'm going to put a negative sign in front of there. Right? And what that does is that just ends up giving me a positive reaction rate. Okay? For products, I don't need to include that minus sign. All right, let's keep on going. Let's say we go another 50 seconds, and now I have 7, and I have 3. And then I look at another 50 seconds, I have 6.5 and 3.5, 6.2 and 3.8, right? So my A is decreasing and my B is increasing. So now I have this data, and I can go ahead and I can plot it. All right, so I'm going to start off with my A starts off at 10. Then at time 50, it's at 8. Then at time 100, it's 7. And then at 150, it's 6.5. And then at 200, it's 6.2. Okay. So this is my data over time. I could go ahead and draw a line. Okay. I'll do this better on the next. I'll actually trust my computer to do it. But notice how it's not a straight line. It kind of curves. Okay, let's do the same thing with my B. So it starts off at 0. At time 50 seconds, I have 2. Then at 100 seconds, I have 3. Then I have 3.5. Then I have 3.8. So it kind of curves up. All right. So I have a decrease in A and an increase. Decrease in A and an increase in B. Right? Here it is. Let me go ahead and erase my stuff. All right. And you can see that. Right now, we have a good curve. This is delta X versus T, concentration over time. We do this a lot of times when we're dealing with different reactions. Okay, so now in this, I can go ahead and I can calculate my reaction rate. My reaction rate is always going to be delta, and we're going to do this for A. So it's going to be delta A over delta T. We're going to put a minus sign in front because A is a reactant. All right, so now between, so let's just do this. Let me think. So if I'm just looking at these first two periods, right, I'm going to go 8 minus 10 over 50 minus 0. And this is going to get me 0.04. Right? Notice between time 50 seconds and 100 seconds, when I do that, I get 7 minus 8 over 100 minus 50, and I get a different reaction rate. And I could actually keep on going, and I would get different reaction rates, right? What's happening is this reaction is slowing down. And this is our rule number 3, that reaction rates can vary with time. Right? And eventually, my reaction rate can even equal 0. This is something we call equilibrium. We'll talk about that in a couple weeks. Okay, so my reaction rates can vary. Right? Now, notice how we're doing this over time. So this reaction rate right here is from 50 to 0 seconds. These are what we call average reaction rates. In the same way that when I was driving from here to Barstow, at 1 second I may be going 90 seconds, a minute later I may be going at one moment in time I'm going 90 miles per hour, the next moment in time I'm going 80 miles per hour, right? It varies, but I can say on average I drove at 85 miles per hour. Okay? This is average reaction rates. Okay, so if I look at this plot, right, the average reaction rate, that's the rate over this time, okay, from 0 to 50 seconds. We can signify this as a triangle. Remember, we dealt with this in Chem 215, but you also in high school, where you can always figure out rate or the slope of reaction by making a triangle, right? Where it's rise over run. Okay, so in this period of time, we can see that over a different period of time, so from 0 to 200, right, we may have a different rise over run or a different rate. Okay. All right, now this slope right here, this is the average rate over that period of time. Okay? Notice how the rate, the average rate, isn't necessarily the same as throughout, right? Here, the rate of change is different than at this point. All right, so we can talk about something being the instantaneous reaction rate. The instantaneous reaction rate is the reaction rate at any given time. We can show this by these blue lines here that show the slope at any given time. Okay? These can differ from the average rate, and they're determined by taking what's called the derivative. Right? The derivative is when I make that delta t that we were talking about, and I make it so small that eventually that delta t goes towards 0. And eventually, once it gets so small, we, instead of calling it delta, which is change, we start calling it just d, where d stands for differential. Okay? Okay, so we have negative dA over dt. All right, so this is my rate when I'm talking about instantaneous reaction rate. Okay, there's one last type of reaction rate we should talk about, and that's what's called the initial reaction rate. The initial reaction rate is that instantaneous reaction rate at time 0, right? So that is in the first second or millisecond or nanosecond of that reaction occurring, right? So that's the slope right at 0, right? So I could do the same thing here, okay? Initial reaction rates become very important. We'll deal with those next lab or next lecture. Okay, so let's look at reaction rates. Now, and let's compare them for my compound A and for my compound B. Now, in the same way I found the reaction rate for A, and remember I have to use a negative sign because it's a reactant, I could find the reaction rate for B. And in this case, they end up being the same. Rate A equals rate B. Okay? This isn't always the case. Let's say I had a different reaction, right? I had A going to 2B. Okay? So in this case, when I go from 10 to 2 molar for my A, I'm going to actually make twice as much of my compound B, right? So I'm going to have 4 molar. In this case, I could figure out my rates. I would get 0.04 molar per second. Whereas here, for B, I'd get 0.08 molar per second. And in this case, they're not the same. Rate A doesn't equal rate B. And the reason for this is because the reaction rate incorporates the stoichiometry. Notice how I get 1A goes to form 2B, right? So what that means is, as I lose 1A, I'm producing 2Bs, right? So I'm producing B faster than I'm losing A. All right, so the reaction rate, we can go ahead and we can have a generalized reaction rate by taking basically the reaction rate and dividing by that stoichiometric term, right? In this case, for A, I divide by 1, because there's a 1 right here, and for B, I get 2, right? And I get 0.04 and 0.04, right? I get the same. This is what we call the overall reaction rate. This is the overall reaction rate. All right, now I can generalize this by going ahead and saying that for any reaction where it's A, where the small a stands for the coefficient, going to B, where the small b stands for the coefficient, in this case it would be 2. It's negative 1 over A times delta A over delta T equals 1 over B times delta B over delta T. Okay? Or 1 over the coefficient for A times its rate equals 1 over the coefficient for B times its rate. We're going to go ahead and do some problems with this, right? So let's say we have this reaction, right? Oh, by the way, this is only for one reactant going to 2 products. But this is the same whether we have something like this, where I now have 2 reactants and 2 products. Okay, so let's go ahead and look at this. Right? We have this reaction. 4NH3 plus 5O2 goes to form 4NO plus 6H2O. Right? We're told that 35 seconds into the reaction, we have a given reaction rate, 4NH3, right? So we have 4NH3, 5O2 goes to form 4NO plus 6H2O. Right? I didn't even include the states because those don't necessarily matter here. They can matter in some cases, but not here. All right, so we're told that NH3 has a rate of 0.6 moles liters to the minus 1 seconds. Remember, this is the same as molar per second, molar per second. However one write it, they all mean the same. Okay, so I want to know the rate of consumption of O2. All right, so let's remember what we said. I said that 1 over A times the rate of A equals 1 over B times the rate of B. Okay? Now, these can be for anything. They can be for reactants or products. Okay? So what that means is 1 over 4, the rate of NH3 equals 1 over 5 times the rate of O2. All right, I know what the rate of NH3 is. That's 0.6. So 1/4 times 0.6 equals 1 over 5 rate of O2. Okay? So I'll move this 5 over. So I have 5 times 4 times 0.6 equals the rate of O2. Okay. I do the math, and this ends up giving me 0.750. That's for my rate of O2. Notice what happened. If I compare the two, right, this is for NH3, this is for O2. The O2, its rate is greater than for NH3. Why? Because the stoichiometry is bigger. All right, so there it is one more time. We can see that first thing we have to do is set up, right, our comparison of the two rates. And then I can go ahead and convert to figure out the rate of my O2. Notice I could do this because I told you what it was for NH3, right? I have to know one in order to figure out the other. Okay, so what I'd like you to do now is to do video problem number 7A. In 7A, you're going to figure out the rate for NO production, and then also for H2O production. Once you get those, go ahead, look at the video, and figure it out, right? And look and try to understand. All right, here is a giveaway. These will be the answers you get, okay? You can go back and you can see that video and understand it, right? Notice that NO is very similar to, or is the same as NH3. Why? Because their coefficients are the same. All right, the last thing I want to do with this is I need to figure out overall reaction rates, okay? So if I want to know the overall reaction rate, what I'm going to do is I'm going to just realize that I can take, I've lost my pen, give me 1 second. I can take my rate and divide by the coefficient, and that's going to get me the overall rate. So in this case, it'll be 1/4 times that 0.6 mole per liter per second. Let me just write it in a way that's a little less confusing. And that's going to get me 0.15 molar per second. Okay? Now, here's the key. If I were to do this with any of the others, let's say I do this with this 0.9 I get here. If I take 0.9 and I take 1/6 times 0.9, what do I get? I get 0.15, right? So for all of these, no matter which one I use, I'm going to get the same reaction rate. All right, so that was chapter 12.1. Now we're going to go ahead and we're going to move on to 12.2, which is a short chapter or section. And this is all talking about what all controls reaction. Okay, so we have these reaction rate rules over here on the left. These are the ones we went over. What factors affect rate? Okay? Now, in order to do this, we need to think in everyday life, right? How do I make a reaction faster, okay, or slower? Okay? Well, the first thing you should know is that rates are affected by what compounds are involved. You can have the same type of reaction, but if it's a different compound, it'll have a different rate. It'll have a different speed. For instance, in 215 lab, if you remember, we did sodium and calcium. We put them in water, and the sodium was explosive, whereas the calcium was only moderately fast. And then we did some things like aluminum, and we barely saw a reaction, right? There was a reaction, but barely, right? So the compounds involved changes that. The second thing we should know is subdivision of reactants, right? The surface area. So let's say I have iron reacting with acid. the acid is going to eat that away, right? This reaction occurs fast if I use powdered iron, whereas if it's a nail, right, it's going to very slow. We know this when we do a chemical reaction in the kitchen, right? If I have something, if I want to heat something up and I just have a frozen burrito, it's going to take a long time. But if I cut it up into pieces, right, it will actually cook faster. All right, the third thing is temperature. Typically, as you speed up a reaction, or increasing temperature speeds up a reaction, typically. This is why we use, in lab, we use a hot plate. And this is why in the kitchen we use refrigerators. Why? Because if I have milk, it's going to go bad, right? But if I just leave it outside, it's going to go bad very fast. But if I cool it down, that reaction rate is going to slow down. And so I can keep it longer. All right, finally, the fourth thing, or actually the fourth of 5, is that concentration. The faster a reaction, or the higher the concentration, typically that means the reaction is faster, right? Let's look at this. A plus B goes to C. Right? We have 2 examples here, right? One, we only have 1 B molecule. The other, we have 5 B molecules. Well, notice for a reaction to occur, A and B will have to collide. Well, on the left-hand side, that only happens every once in a while. But on the right-hand side, that's going to happen more often, right? So the higher the concentration of reactants, the faster the reaction. All right, the last factor that we're going to say affects rates is what are called catalysts. Catalysts are a substance that increases the rate of reaction without being consumed. Okay? They do what we call lower activation energy. We'll talk more about this next week. But remember from 215 we said, hey, sometimes a catalyst is involved and we just put that catalyst, what is involved, on top of the arrow. Okay? This isn't involved in the reaction, but it makes it go faster. All right, so that is it for lesson 7. Remember, on Monday, April 20th, I'll post a video on the quiz and test procedure. Your quiz number 1 will be on Wednesday, 4/22. Okay? On Friday, 4/24, will be a review. And then on 4/27, there will be test 1. This is on sapling. There's no homework for this lesson, lesson number 7, but some of these questions may be on homework number 8, which will be due April 20th. All right, with that, I'll talk to you later. Have a good day.